From automated assembly lines to surgical suites, robotic manipulators are transforming industries and our daily lives. These mechanical marvels are no longer confined to science fiction. They are now essential tools in a wide range of applications. Imagine a world where robots handle dangerous tasks, perform intricate surgeries, and assist with everyday chores. This is the promise of robotic manipulators, and their importance will only grow in the years to come. But, how do these complex machines work? What are the secrets behind their precise movements and sophisticated capabilities? This exploration delves into the fascinating world of robotic manipulator dynamics. It aims to make the complex concepts of kinematics, dynamics, and control accessible to a wider audience. Whether you're a student, a tech enthusiast, or simply curious about the future of robotics, this journey promises to unlock the secrets behind these incredible machines. Join us as we unravel the principles that govern their movements and explore the mathematical models that bring them to life. Before we dive into the intricate world of manipulator dynamics, let's first understand what robotic manipulators are and their key components. In essence, a robotic manipulator is a machine resembling a human arm designed to perform tasks in various environments. These mechanical arms consist of several rigid bodies called links connected by joints. These joints provide the manipulator with the flexibility to move and manipulate objects in its surroundings. Think of the manipulator as a chain, where each link represents a segment, and the joints act as connections, allowing for relative motion between them. These joints can be rotational, like our elbows, or prismatic, like a piston moving in a straight line. Each joint is driven by actuators, which can be electric motors, hydraulic systems, or pneumatic systems. These actuators provide the force and motion necessary for the manipulator to perform its designated tasks. At the end of the manipulator's arm is the end effector. This crucial component acts as the robot's hand and interacts directly with the environment. The end effector can be a gripper for grasping objects, a welding torch for industrial applications, or a surgical instrument for medical procedures. Understanding the basic components of a robotic manipulator provides a foundation for grasping the more complex concepts of kinematics and dynamics, which we will explore in the following sections. Kinematics is the study of motion without considering the forces causing it. In the context, kinematics focuses on the relationships between the robot's joint angles and the position and orientation of its end effector. Imagine you want the robot to pick up an object. Kinematics helps us determine what each joint needs to achieve to position the end effector correctly. This involves understanding the geometry of the manipulator, the lengths of its links, and the types of joints connecting them. We use transformations to represent the position, orientation, and velocity of the end effector in relation to the robot's base frame. Forward kinematics, a fundamental concept in robotics, deals with position and orientation given the joint angles. Conversely, inverse kinematics focuses on determining the necessary joint angles to achieve a desired end effector pose. Kinematics plays a crucial role, ensuring that it can reach its target position without collisions and perform its tasks accurately. It forms the foundation for understanding the more complex aspects of manipulator dynamics, which we will delve into next. Section 4. Dynamics, the forces driving robot motion. While kinematics describes the motion of a robot, dynamics delves into the forces and torques that cause this motion. Understanding manipulator dynamics is crucial for predicting the robot's behavior under various conditions, such as different payloads, speeds, or external forces. Dynamics considers the inertia of the robot's links, the forces exerted by the actuators at each joint, and any external forces acting on the manipulator, such as gravity or contact with objects. By analyzing these forces, we can derive equations of motion that describe how the robot's joint angles change over time in response to these forces. These equations are typically complex, involving differential equations and matrix operations. The field of dynamics is essential for designing robust control systems that can precisely control the robot's movements, even in the presence of disturbances or uncertainties. It allows us to determine the necessary actuator torques to achieve desired accelerations and to ensure the robot's stability during operation. In simpler terms, dynamics helps us understand why the robot moves the way it does and how we can influence its motion through control inputs. Section 5. Taming the beast control in robotic manipulators. Control theory plays a pivotal role in governing the movements of robotic manipulators, ensuring they execute tasks with accuracy, speed, and stability. Imagine trying to make a robot arm follow a specific path. Without a control system, the robot would move erratically, unable to account for inertia, gravity, or external forces. Control systems provide the necessary intelligence to regulate the robot's motion. They continuously monitor the robot's current state, compare it to the desired state, and calculate the appropriate control signals to be sent to the actuators. These signals adjust the forces and torques applied at each joint, guiding the robot along the desired trajectory. There are various control strategies employed in robotics, ranging from simple PID controllers to more sophisticated adaptive and model predictive control techniques. The choice of control method depends on the complexity of the task, the desired performance level, and the robot's characteristics. Effective control is essential for robots to interact safely and efficiently with their environment, whether it's performing delicate surgery, assembling intricate components, or exploring hazardous terrains. Section 6. Precision in action and effector control. While controlling the individual joints of a robotic manipulator is essential, the ultimate goal is often to precisely control the motion of the end effector. This is especially crucial in tasks requiring high accuracy, such as welding, painting, or surgery. End effector control focuses on manipulating the position and orientation of the robot's hand in space, regardless of the individual joint movements required to achieve that. Instead of directly controlling joint angles, we define the desired trajectory of the end effector in Cartesian space. This could be a straight line, a curved path, or any other complex shape. The control system then utilizes inverse kinematics to determine the corresponding joint angles needed to achieve the desired end effector motion. This approach simplifies the control problem, as we can focus on the task's geometric aspects rather than the intricacies of individual joint movements. End effector control enables robots to perform complex maneuvers with ease, such as following a curved surface while maintaining a constant force or inserting a delicate component into a tight space. It significantly enhances the robot's dexterity and precision, making it suitable for a wider range of applications.